While they're changing places, I will introduce the next speaker, which is Boris Čule. Boris is an assistant professor at CSAI. He has a PhD in computer science from the University of Antwerp. He was also a postdoc there for a while. He is a rather popular lecturer in our Master Data Science and Society. In particular, the course on big data analytics is one that is highly appreciated by students. His research focus is on sequential pattern mining, where he introduces novel measures to evaluate patterns. He also worked on broadly relevant topics such as anomaly detection in time series. Discovering anomalous patterns is in a complex heterogeneous time series data is interesting as a high range of applications, but this is not an easy task. To give an example of the difficulty, an outlier in such a data set can represent an important source of information, but can also be rather spurious or irrelevant for the task at hand. Today, Boris will talk about pattern-based time series classification. Boris, the floor is yours.
So good afternoon, everyone. Welcome to my talk. As Peter said, I will be talking about a pattern-based time series classification. That's quite a long title, full of terminology that I will now try to unpack. So I will start off with a general introduction about time series data, what classification is, and a little bit about pattern mining before describing how it all comes together. This presentation is largely based on a recent publication of mine, together with a couple of colleagues from the University of Antwerp. So let's get going with some basics. First of all, what is time series data? Time series data is defined in a fairly simple way as an ordered sequence of values, typically real numbers, which come at regular temporal intervals. So that's a fairly broad definition of what a time series is. As Peter said, time series are encountered in a variety of settings all over with a variety of applications in the real world. So, for example, sensor readings, whether that be weather data, temperature, pressure, whatever else. Sensors could be measuring GPS data, trajectories, motion sensors, but also other types of data such as medical data, stock exchange data, etc. So I will be talking today mostly in fairly generic terms, describing methodology and algorithms rather than talking about a particular application. But what I will be presenting has wide variety of application and possibilities to be applied in a variety of settings. There are different types of time series. We call them the three different use cases when we talk about time series. The first is a simple case, the univariate time series, where your data consists only of a single sequence of values. So, for example, a single stock price, where your data set could then contain multiple stock prices, which are each considered a univariate time series. A more complicated problem setting is where your data consists of multivariate time series, where you have several time series linked together and forming some sort of entity. So, for example, if you have a machine which is connected to several sensors, and those sensors measure all kinds of information about that machine. Like I said, it could be the air temperature, it could be the temperature of the machine itself, It could be some kind of throughput or energy generation or energy consumption. So all kinds of things that are measured about the same machine at the same time, at the same regular intervals. That way we obtain a multivariate time series. And finally, the most complex type of data that we could have is the so-called mixed type time series, where in fact, you don't only have a time series as I've defined it on the previous slide. So you have uni or multivariate time series, but you are coupling them to some event log data. And again, event log data is something very generically defined as a sequence of events. And this sequence of events doesn't necessarily have to contain, let's say, real valued measurements, doesn't even have to contain numerical data, and doesn't even have to come at regular time intervals. So that adds to the complexity of the problem. An example of this is, again, you have a machine, you have some sensor data being collected about that machine, but you also have an event log, a log of, for example, what a machine operator does with that machine, which can happen at all kinds of irregular time intervals. For example, why is this relevant? Well, this information, of course, can inform us about the time series data and inform us about how normal or abnormal the time series data is, and can add to the patterns that we can find in the time series. To give a trivial example, if you are measuring the output of a particular machine and all of a sudden the output drops to 0, you might think there's something wrong. But if you couple this with an event log data, which tells you that the machine operator at that moment switched off the machine, then of course this is perfectly normal behavior. And by combining these two sources of information, we are perhaps able to gain insights that we otherwise wouldn't be able to do. The next bit of terminology that I have in the title of the talk is classification. This is again a fairly simple concept that is perhaps known to most of the audience. So I will just very, very quickly sum up what we mean by classification. Essentially, classification is the process of learning from a training set and applying this knowledge, what you've learned on the training set, to classifying new instances of data. I give here a nice example, let's say not directly a time series example, an example of image classification, where we have images of 4 different classes of animals in this case. We have beetles, we have flies, we have birds, and we have chickens. So from the small training set that is there, we could try to learn how to classify new instances. And when a new instance comes in, we want to assign a class label to that new instance based on what we have learned from the training set. Now, of course, how does this tie in with time series? Well, we can in the same way classify time series. Of course, the problem becomes a little bit more complex because time series come in all sorts of shapes and forms, and even time series of the same class, as we can see on this example, can be quite varied in comparison to each other. So what is the goal of time series classification? What is the goal of learning? What do we want to learn from a training set in time series classification? Well, we want to learn 2 things. What makes time series of a particular class similar to each other? That will allow us to assign a particular class label to another new time series that is potentially similar to known time series of a particular class. But also, what makes time series of a particular class different from those of other classes? So again, to give a simple example, if you find a particular feature that is present in all time series of a particular class, that feature might be useful for classification, but it might not be. If that feature is also present in time series of other classes, then that feature is not very useful for classification. So we try to find frequent patterns, as we will see, in different classes of time series. We try to see which patterns are good for discriminating between classes and which patterns are not, and those ones we don't use for the classification task. So how do we do time series classification? Well, there are two approaches and two types of algorithm in general. You can compare time series directly to each other. So you can feed the time series into an algorithm, and the algorithm then produces a classifier. Or we can try to transform the time series into feature vectors that somehow describe the time series. And that way, we can then compare those feature vectors to each other, and in that way, learn a classifier. Here is a small example again, where we see, I think, 2 time series from 8 different classes, each class of a different color. They are sequentially ordered, so the first 2 are from the same class, the third and fourth are from the second class, etc. We can see the original time series on the left, and we can also see what happens if we simply apply a nearest neighbor classifier on the raw time series data, and we can see that it goes wrong. Even though visually these time series are quite clearly similar to each other, the ones that are in the same class, a nearest neighbor classifier would struggle with this if you just use Euclidean distance point by point, for example. So this is in itself not a good idea. So what we do, that's the middle column there, and on the right column, you can see what another method does, which does a similar thing to what we do. So what we do is we transform the time series into feature vectors, and then we compare the feature vectors to each other. And you can see here on these plots that the feature vectors actually of the 2 time series that belong to the same class are always quite similar to each other, and are in fact, in this very, very trivial example, always the first nearest neighbor of each other. So how do we do this? Well, we do this by mining patterns in time series. And what are patterns? Well, we look for reoccurring sequential patterns in time series data. So we take the time series data, we find reoccurring patterns in them, and then we want to use those patterns to answer those 2 questions that I've asked a few slides ago. So the intuition behind our method is that if a new instance, a new time series contains the same patterns as known time series of a particular class, then the new instance has a high probability to belong to that class. If the instance doesn't contain the same patterns as other known time series of a particular class, then it's less likely to belong to that class. So we aim to discover discriminative patterns for each class, and then we classify new instances by essentially checking whether the new time series has known patterns of all the classes and whether it lacks the known patterns of all the classes. And by doing that, we can compute to which class the new instance most likely belongs to. How do we build the feature vectors? Well, essentially, each pattern that we mine, that is discriminative, that we decide to keep, we use it as a feature. So the embedding of a time series data into feature space essentially produces a matrix. In this matrix, each time series is a row, and each pattern is a column. And then we try to see which patterns are found in which time series. We assign, if we look for exact pattern matching, we assign 1 if the pattern is present in a time series and a 0 otherwise. We also experimented a little bit with an alternative method, which used approximate pattern matching, where we define the similarity between each pattern and its nearest occurrence in the time series. In all these examples, and during the talk, I'm talking about, I'm giving examples of univariate time series, but everything that I've theoretically mentioned can also be used for multivariate and mixed type time series. A word about interpretability of our method, which is also important in classification, so that users of algorithm also get some feedback on why a particular classification took place. I'm giving here back the example of beetles and flies. An interesting example because it also shows that what is at first glance not a time series can be turned into a time series. And then, of course, you can utilize time series classification methods that you would otherwise might not be able to do. So what we do here is we take the images, we take their outlines, and we convert them into time series by essentially measuring the distance from each point on the outline to the center point of the image. And that way we obtain time series by essentially rotating along the image outline. An interesting note, you can also see here that when we talk about a time series, the actual x-axis doesn't have to represent time. So we did this on this example data set. We classified the time series, and we can convert them back into images doing the same way. And what we can do, when I say producing feedback, we can see here on the visualization, we have two classes of objects, beetles and flies in this case. And we have actually visualized patterns that we have associated with beetles in blue and patterns that we have associated with flies in red. And we can see that in this small data set of 20 animals, 20 insects, we actually got 3 of them wrong. And we can see exactly why we got them wrong. So in the first row, the second image, we can see that we classified it as a fly when it's in fact a beetle. And highlighted in red on that image are the patterns that we found in that image that are normally associated with flies. So by analyzing the results of the classification in this way, you can get insights that you otherwise might not be able to obtain. Very quick word on the evaluation because I'm running out of time. So we have compared our classifier with tens of other classifiers on hundreds of data sets. And of course, all the evaluation that we can do, we can talk about average results. What was for us important was the interpretability. That was our main motivator for this work. We have a classifier that's fully explainable. We also have a classifier that's applicable to all 3 use cases that I mentioned, so univariate, multivariate, and mixed type data, which for which there are not a lot of other classifiers available. We have a relatively fast method, in fact, faster than most existing algorithms because it's relatively simple and based on pattern mining. And finally, we have a classifier that produces very good accuracy results. So like I said, we're talking about averages here. To our surprise, our method didn't do much worse than the best deep learning methods. It did do slightly worse. I say narrowly outperformed, but we did test on hundreds of data sets. And in fact, in about a third of them, our method outperformed the deep learning methods, which was quite, we were quite positively surprised by that. And our method produced higher accuracy than any other pattern-based method. So to summarize, I give a very small summary of how the method works on univariate, multivariate, and mixed type time series. And I think my time is up with that. So thanks for your attention. I'm happy to answer any questions.
Thank you. There is one question in the chat, actually 2 already, so that's a quick one. So can you elaborate a little on the feature factors? How is a certain pattern chosen to be put in the matrix?
Okay, so first of all, we have what I said on this slide. We are looking for discriminative patterns for each class. So we mine all frequent patterns, and then we see which ones are discriminative. Like I said at the previous example, patterns that are present in all classes are not particularly useful for classification, but patterns that are present in a single class and not present in other classes are. So that's what we mean by discriminative patterns. That's how patterns are selected. And then we have essentially an embedding. Then we know which patterns represent the columns in that matrix. And then we look at a row by row basis. So we are looking at the time series that we have, and we check whether those patterns are present in a time series or not. I don't know if it was the scope of the question. How do I fill in the matrix? In other words, where the values come from. So like I said, we have tested actually a number of variants of our algorithm, but I didn't have time to go into that. One variant worked with exact pattern matching. So purely binary. The value would be 1 if the pattern is present in the time series. The value would be 0 if the pattern is not present. We've also experimented with approximate pattern matching, where we said for each pattern, we try to find the best match in the time series. We then measure the similarity between the pattern and the best match, and then we assign that value. So then the vectors are no longer binary, but the vectors actually contain values between 0 and 1. So real values between 0 and 1. The higher the value, the better the match.